absolute value of that, that's just omega A. Here, the maximum value, that's when omega t, say, is going to be equivalent to 0. That's just omega b, where b is just another amplitude. And that's why your book quotes the maximum velocity of an object undergoing simple harmonic motion as omega, the angular frequency, multiplied by the amplitude. You can call it A or you can call it B. They both mean amplitude. With that in mind, acceleration is the change in velocity over the change in time. But what that means is acceleration really is the time differential of the velocity. And if we do that once again, so going right here, that means the acceleration is going to be, in this case, minus omega squared A cosine omega t. And for over here, it's going to say the acceleration is minus omega squared B sine of omega t. Which in both of these, this is just saying it's going to be equal to negative omega squared times the position. And over here the same thing, negative omega squared times the position. Because notice, it's negative omega squared multiplied by A cosine omega t, that's what we had here. Negative omega squared times B sine omega t, the same thing. And thus that's the values that we get. But once again, if you want to find the maximum value of the acceleration, the maximum value of the acceleration, the absolute value, is when omega t, in this case, for cosine is equal to 0. That means it's equivalent to 1, and this is just omega squared times the amplitude A. For here, the maximum acceleration is just going to be, once again, absolute value. In this case, it's omega squared b, omega squared times the amplitude. So that's why your textbook quotes the maximum velocity as omega times the amplitude, and the maximum acceleration as omega squared times the amplitude, where the maximum is just pointing in this position or this position or here. So that's what it's referring to in each of these cases. So that's how we get that. But they may ask you in particular for, say, what the average power is or energy is or anything like that. So let's look in particular for a spring for a moment. So if we use the example of a spring, the potential energy of a spring is 1/2 kx squared. So if you wanted to find what that is, let's say that its x was A cosine omega t. Let's just throw that in, because x is just a position. And remember, the spring just means it's oscillating back and forth. So its position at any time t can be given, say, by A cosine omega t. So if I write that, this is equivalent to 1/2 k, and here let me put in here A squared cosine squared omega t. Which tells me that the potential energy of the spring is changing at any given point. Because notice at each point t, the value of cosine is changing, and thus the value of cosine squared is changing. But here's an important part. Whether this was cosine, or even if this was 1/2 k A squared sine squared omega t, cosine and sine share something very similar to each other. Let me draw their values here. So if this was, say, sine squared, so by sine squared, I'm just doing sine, not A sine squared, just sine squared. That means it's going to be bound from 0 to 1, or same for cosine, 0 to 1. Looking at that, remember, this is what a cosine looks like, but a cosine squared is going to look like this. And if we just continue it on and on, this is basically what it looks like. Sine squared is going to look like this. And if we continue it through multiple oscillations, this is what it's equivalent to. If you use calculus and integrate it over an extended period of time, you would find what the value is. Or, simply put, we can just find what the average value is. So either doing the strict calculus definition of integrating over infinite time to find what the value of sine squared or cosine squared omega t is, or by finding the average value, what we would find is that sine squared omega t is equal to cosine squared omega t, which is going to be equal to 1/2. That's what it's equal to. And notice it's bound between 0 and 1. And thus for this, if we look back here, this is equal to 1/2. This is equal to 1/2. And that's why you would get for both of them that this is just going to be equal to 1/4 k, the maximum amplitude squared. And I believe when you did your lab, I think with the spring, this was one of the results that you were supposed to get, what the potential energy was, or they did that in the derivation. But it basically just becomes 1/4 k a squared, and that's just because sine squared or cosine squared, if you do it enough times, which really means if you just let that spring go back and forth for many oscillations, so that just isn't one oscillation, but many oscillations, the average value of cosine or sine squared is the same, it's 1/2. And thus 1/2 kx squared, 1/2 k a squared, either cosine or sine squared, just reduces to 1/4 k a squared. And that's the basic idea for this simple harmonic motion. And just to give you a picture for this, what this basically means is that this was x of O, the equilibrium position, and I extended it at a distance x here, x is equal to a. And thus it would compress the distance x, and x is equal to a. So that's what it means, the maximum displacement for a spring. That's what a would be. So if you just extend it by a centimeter, a, the amplitude is a centimeter, the maximum amplitude. And so this is the end of simple harmonic motion, where I just wanted to complete. I've already derived where we get these equations. I've derived how the basic idea between forces and torques gets you to those equations for a spring and a pendulum. And here I just want to show you that the velocity and acceleration are gathered by these equations. Maximum is omega a, omega squared a for either of them. And for energy, anytime you have cosine squared or sine squared, and you're doing it for many oscillations, that just reduces to 1/2. And that will become very important, especially next term when you deal with physics 2200.